So probably we can move on with the next part of the tutorial. And I just wanted to say that even if you did not finish this exercise, the web page will be up and running, will be there. So you can really do this tutorial at your pace when you come back. As well, you will find also other tutorials if you want to explore more the capabilities of the code. And so maybe now we can move on.
Yeah. Let me add a couple of things. The other tutorials that Daniele mentioned, many of them, they are designed to be run on your local machine. So you can also do tutorials with very small systems in which you explore more the post-processing, but less the parallel part, and you run on your machine. So this also can be useful, right? Okay. And so, for example, one possibility, you see that if we would continue the GW tutorial, apart from encouragement to test different parallelization schemes, there is also an optional last part that would be the full calculation of the GW corrected quasi-particle band structure, so the band gap correction of the DFT problem. This is a longer calculation that, if you do it, in the end will lead you to this plot, or similar, I hope, which is a comparison of the DFT band structure that you calculate, in this case calculated with quantum espresso. You see, for those who know a little bit more, you see that we have fully included spin-orbit coupling in this calculation, as evidenced by the splitting in these bands. And that is included also in the GW calculation. And the GW bands are the solid lines. So these are not converged. But again, if you're interested in this type of systems, notice this. This is not just a shift. Okay, it's not that we take the conduction band, we do plus 1 electron volt. Look at these valleys at the K point and at the middle between gamma and K, that is usually called lambda in the literature. In DFT, the lambda valley is at higher energy than the K, and so this is a direct band gap material. In GW, in this calculation of GW, the lambda valley is below the K. Why? Because the self-energy matrix element at this nk point has a smaller value than this. Why? Because the bond orbitals, the orbital character of the wave functions at this point are different than here, and so the integrals are different. So according to this calculation, monolayer MOS2 becomes an indirect bandgap material. Now, is this true? Or is it like an artifact of this calculation, or of the pseudo-potential that we use, or of the lattice parameters that we optimized? These are the type of problems that cannot be solved by just pressing enter and doing the calculation, even though doing the calculation is not so easy, as you have seen. And typically cannot really be solved so far by automatic workflows. This is one of the reasons why it's so difficult to make, at least up to now, machine learned models for excited states, because many systems are fragile with respect to both the experimental setup and the simulations. And you can have these things and you don't know if you are correct or not, but the physical properties are really different, because indirect and direct system is very different. So I give you the answer. No, it is not correct. If we do a better calculation with better lattice parameters and better convergence, the lambda valley will go back above, but the difference between the two is much lower than you would find in DFT. So it's almost close to being direct, but remains direct. So that's just an example of the subtleties that you have. And like you have to be, know very well your system, not just know the code and HPC, but in this type of material, you also know very well what is going on. Okay, so after this, we can, if you want, I will go, if you want to follow, we change topic and we go to optical absorption. So it was the second topic for our many body days. And so if we go back to the Kobe page, the Kobe main page, we go down. Now we have the second link with the complete tutorial, and we can click, and we go back on the Bethe-Salpeter equation. So we also had a reminder before. The goal of here is to run a Yambo calculation to, first of all, build the two-particle Hamiltonian, that we discussed, and then we will try to diagonalize it in various ways. And from the eigenvalues and eigenvectors, we will be able to plot the optical absorption of the system, including the effects of strong electron-hole interaction, including the presence of excitons. And okay, so you can start going on this page and reading a little bit the requirements. I will give you some minutes, just one thing. I will go in the directory and show you. Okay, this is really bad. Let's go in another. Okay, so the first directory of the tutorial is the 01 BSE Hamiltonian. You see here, here you find again the save directory, which is the basis to run Yambo. You find a submission script that I invite you to check. And then we already have this directory that contains the results of the GW calculations from the previous tutorial. So if you finish the last step of the previous tutorial, in principle, you could use your own calculation. But just in the interest of time, I provide here already the calculation done. And if we inspect this directory, you see all these files. These are binary, non-human readable files that contain the microscopic dielectric function, which is PP, and contain the dipoles, which is dipoles, and then contain this new database ndb.qp. This contains the GW energies. So this contains the output of the GW flow, the GW workflow, right? And now this will be included, imported inside the Bethe-Salpeter workflow for absorption. So you don't need to, in principle, if you start from scratch, you should calculate all of these. But actually, you don't need to do that. You can only do the Bethe-Salpeter step. And in fact, if you check, if you check the script, you see that and running, when we run our input, note the input is not there. So you have to generate it like we did yesterday for the GW part, right? But when you do this and you run it, you see that with -j, we include the previous directory. This means that Yambo first goes here and loads all the GW calculation, okay? And then creates a new directory that we call BSE and puts the BSE calculation inside this directory, as well as all the report files that we have seen are very important will also be put with -c in the same directory, okay? Okay, now I just invite you to read the first part of the tutorial and try to generate the input, and I will pull up the input part of the tutorial. Remember that to generate the input, you have to go on an interactive node, okay? Okay, yeah, here there is something, okay, you have to go on an interactive node, okay? Let's actually do it. So here, instead of copying the command all the time, I have an alias that I called node. So I show you, if I do this, you see that when I type node, I'm actually giving all these long command. So this is just convenient. Okay, now I'm entering the interactive node. Remember two things when you are in the interactive node. First, that you need to load Yambo. Otherwise, the cluster doesn't have the executable, doesn't know where Yambo is. So now we will do it. So you see that in the submission script, we have the indication how to load Yambo. You might notice that this is a different export path than before. This is because this is a different compilation of Yambo. Let's not enter into this for now. Just in this case, in order to load Yambo, you have to export these two lines, which I have done. And now if I do which Yambo, yeah, you see that we have it from William's directory. Okay. And the second thing to keep in mind, when you run it in the interactive node, you have to use MPI exec, right? Before to perpend it to the Yambo command. This is a detail of Fugaku that we need to obey, let's say. Then do the input part, generate the input, modify the input variable as explained, and then we discuss a little bit what they mean. And then you can exit the interactive node, because then we will submit the simulations, as always, from the front end.
Can I just have one smile from everyone? 1, 2, 3, smile. I have a quarter of your face. Is that okay?
It's okay.
Thank you. This is the track that's most difficult to take photos because you are so engaged. So please enjoy.
Okay, you see here we are giving different flags, of course, to the Yambo executable in order to generate the input, because now we are doing a different workflow, if you want. So we are doing -O is just minus optics. So we are doing an optical absorption calculation, and B is BSC. So this instructs Yambo, we are doing BSC. Then we are giving all the other information, so what type of screening it should take, which type of kernel it should use for the excitonic Hamiltonian, and we use the standard for exciton, which is HART3 statically screened exchange. And then we say that the input file will be called bsc.in. We turn on maximum verbosity, because we need some variables that only will appear if we turn verbosity on. And there is a new thing, you see, we can give minus big J also to the input generation. And we indicate the directory where the GW calculation is. This makes it so that Yambo reloads the databases there and automatically puts in the input files the values that correspond to the calculation that you have done. So you don't have to input all the values for the screening. They will appear already correct in the input because they are read, because you have already calculated that. And you can tell Yambo to do this with -J. So if you run it, then you will have an input file. Again, as we have seen yesterday, you have the run levels, and this time will be different types of run levels. The most important one, as you can see, is optics, and then BSE for Bethe-Salpeter equation. Then we have the new variables for the Bethe-Salpeter equation, which the most important ones and the ones that we need to modify are basically 3. Two are related to the cutoff values of the components of the beta saltpeter kernel. What does it mean? It means that if we go to the equations, you see that to build the kernel, we need V and W. W and V are this. And as you can see, they are both sums in a reciprocal space over G vectors. This is, of course, are infinite sums. We cannot sum over infinity. We have to cut off the sum at a certain point, and hopefully the quantity has already converged to the final number. This is something that in a real calculation you have to check very carefully, because on the one hand you want to put as low cutoff value as possible, so the calculation will be faster and will need less memory, which is critical. On the other hand, you want to have high as possible, so that the number that comes out for this matrix element is actually accurate. So now, of course, we are not doing this test that I suggest to do with automatized scripts or workflows, and not to do by hand because it's very boring. We are putting some values. By the way, this second value is already the correct value, while the first value is already not correct, should be increased more. And the third quantity gives you, basically, it what determines the size of the matrix. So if you remember from yesterday, the size of the matrix is given by basically the size of these three components. The number of k points with which we sample the reciprocal space, and this is fixed by the DFT calculation. So we did a DFT calculation with a certain grid of k points, and this is fixed. Obviously, this is a convergence parameter. Maybe this grid is not dense enough. Then we need to rerun the DFT calculation with a finer grid. Okay, and then the other two labels are the occupied states, valence bands, and empty states, conduction bands. And these two, we are specifying them in the Yambo input, because maybe in BSC we did calculation for many bands, but we don't need so many in the beta saltpeter Hamiltonian. Actually, typically you need very little, just the top valence bands and the bottom conduction bands. And so here, we are selecting from band 23 to 30. What does it mean? Well, if you check the setup file when you generated the save, there was an indication to do this yesterday, you realize that in this system, the top of the valence band is the number 26, okay? And then there is the band gap, and after 27 is the first empty conduction band. So here we are including 23, 24, 25, 26. Yeah, and so you are including all these valence band, and then 27, 28, 29, 30. We are including also 5 conduction bands. So we are including 5 valence bands and 5 conduction bands, or 6. Yeah, maybe I counted wrongly. So this is the idea, and these are the most important variables to put in the input, right? I'm telling you this, but it's also written in the text. And then we have another important thing, which is this string. This variable will be generated in the input, but you have to then edit the string. And this will tell Yambo to read the GW energies from our previous calculations. It's telling it, okay, take the energies from this directory, this database. And so this is always the name of the database for GW energies. If we add this, it means that now the excitonic Hamiltonian, in this diagonal part, these epsilon energies are the GW energies. But if we don't do it, it will use the DFT energies, okay? Okay, and that's basically it. And finally, we have another couple of variables for the parallelization. Now you know very well how it works. Of course, also the kernel of the BSC can be parallelized in several respects. Typically, the most efficient is K. So here we are using for this calculation 4 nodes, so a total of 16 tasks. And we are distributing them 8 on K and 2 on this T index. This T index corresponds to this CVK 3 turn of labels. So one T is one CV couple, basically. Okay, so that's it. So please complete the input. And then when you are ready, you remember you exit the interactive node and you can run this job. And this job builds the excitonic Hamiltonian. There will be no human readable output apart from the report. And so that you should check. But if everything went correctly, inside the BSC folder, you should have this database. Okay? And this contains the excitonic Hamiltonian, not diagonalized. We just build the matrix, we still have to diagonalize. Okay, so were you able more or less to run the first run for the BSC? So generating the first input and then producing the first results here in this database? Okay. I assume yes. Yeah, that's true.
Can you raise your hand who has finished the first run? No, I don't know if you have this, but no, wait. This is the Fujitsu compiled. And for this, if you go to the tutorial page, for this tutorial, you need to load the.
You can, if you look, you see that this. Yes. So just let me repeat something. Here we are using a different compiled version of Yambo than we were using for the GW calculation. So in order to load it, we have to export a different path. And the path, you can find it inside the submission script for this calculation. You see, it is these 2 lines. So it's a bit different than before, okay? So also when you go to an interacting node, you have to use this version of Yambo. Actually, no.
The same.
Exactly, it's not true actually, but so to generate the input, you can generate with whatever compilation you want in reality. Yes. So just let me repeat something. Here we are using a different compiled version of Yambo than we were using for the GW calculation. So in order to load it, we have to export a different path. And the path, you can find it inside the submission script for this calculation. You see, it is these 2 lines. So it's a bit different than before, okay? So also when you go to an interacting node, you have to use this version of Yambo. Actually, no.
The same.
Exactly, it's not true actually, but so to generate the input, you can generate with whatever compilation you want in reality. So are you experiencing problems where your jobs are stuck in the queue and do not run immediately? You, yes? Anybody else? Okay.
Sorry, we just realized if you run the script, in the script you assign 2 nodes, which is fine, but it will take some times, the order of 15 minutes. Let's use more nodes, at least 4. And yeah, it scales quite well. And so in 5 minutes, less than 5 minutes, the run should finish. So 2 minutes. So yeah.
This is the submission script. When you open it, you find number of nodes equal 2, this is a typo. I apologize. It should be 4, okay? If you put 4, it becomes consistent with the text of the tutorial because you see here in the parallelization, it is suggested to take 8 times 2 tasks equals 16. Therefore, it is 4 nodes. Sorry that I did not realize that there was a typo in the submission script. You simply change it from 2, which is what is written there, to 4. That's it. And then you submit the simulation. In this way, it lasts 2 minutes. Otherwise, with 2 nodes, it will last kind of, I don't know, 15, 20 minutes. Yeah. Okay, so in the remaining time, let me just walk you through the rest of the tutorial. And then you have time to continue until the end, which will be formally at 2020. So, but just so that you see everything, I will just summarize everything now, okay? So after you build the excitonic Hamiltonian, so now you have, after the first part, you have a database binary file that contains this quantity, equation 1. But this quantity has off-diagonal matrix elements, so by definition it's not diagonal. We diagonalize it. And the diagonalization happens in the second step of the tutorial, which is here, solve the excitonic eigenvalue problem. So what we have to do, this is the eigenvalue problem. What we want to find is this E, the eigenvalues, and these are the exciton energies. The physical meaning of this is the energy of the exciton. And then the eigenvectors, A, also, we want to find them because they are related to the exciton wave functions. And then the first thing that we can do with eigenvalue and eigenvectors is to plot the absorption. And then we can do even more post-processing when we have these quantities. So here, as we discussed yesterday, of course, diagonalization is a lengthy business. And in Yambo, you have 3 approaches, right? Either you diagonalize fully this Hamiltonian, which is the slowest possible approach, but it gives the full absorption spectrum, all the eigenvalues, all the eigenvectors. Otherwise, there is the fastest approach, in which you use an iterative algorithm based on Lancho's algorithm called Haydock to iteratively diagonalize this. This will give you access to the absorption spectrum, but you do not have the eigenvalues and eigenvectors, but it's the fastest way to get the absorption spectrum. And then there is the best of both worlds, which is an iterative solver in which you can specify how many eigenvalues you want. That gives you really these eigenvalues and eigenvectors also in addition to the spectrum, okay? And so in this part, basically you have to try all 3 approaches. So full diagonalization, iterative solver only with the spectrum, and iterative solver also with eigenvalues and eigenvectors. To do this, you can create 3 different inputs, starting from the initial input. And then here in this part, it explains what changes. It's the addition of a neural level, BSC solver. And then for each of the 3 cases, there are some specific variables that you can set. For example, BSS mode H is the iterative Haydock solver, the one that gives only the spectrum. Or BSS mode D is the full diagonalization. This uses LAPACK. Okay, this is just a call to LAPACK to diagonalize the matrix. Or scale-up, but let's say that the performance is not extremely improved, but yeah, it can be also a call to scale-up, scale-up, and then all the other possible libraries. For example, on GPU can be Magma and so on. And then the third is BSS mode S for SLEP-C, which is the specific library that we are using in this case for iterative diagonalization, including eigenvalues. And in fact, here you see we have an additional variable in which we specify how many eigenvalues we want. So in this case, we put 10. And then we will see what happens if we plot the spectrum with just the first 10 eigenvalues, right? So if you continue, there are some other details that you can read about in the input files. And but let's say you run all these 3 inputs, and then the code doing the job will diagonalize the matrix in these three ways and will produce a new output file. And this output file is going to contain the absorption spectrum. That is the macroscopic dielectric function, okay? And then you can plot it. Finally, this is a result that we can plot. So there is a GNU plot, you can do with GNU plot. You can just copy-paste this script, or you can do whatever you want. Basically, the output has columns. One column is the energy, another column is the imaginary part of the electric function, which is related to absorption. Another column is the real part. And then you also have additional columns for the case of no excitons. So you can plot the case with and without excitons and compare. And here is what you should get if you run this. So these are the results for the three algorithms. This is the absorption spectrum of molybdenum disulfide. And you see that the iterative one, which is the black, and the full diagonalization with LAPAC, SCALAPAC, blah, 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 they are exactly on top. Okay, so, but if you check the timing, the Haydock part is extremely fast. It's like 1 order of magnitude faster to obtain the same result. So, of course, it is better. However, it doesn't give you the eigenvalues, remember. What about this one, the SLEP-C? In reality, this is also correct. The fact is that we only included the first 10 eigenvalues in order of energy. So it arrives to the first 2 peaks and then stops. If we include more, if we include the first 100 eigenvalues, for example, of the matrix, which is thousands in rank, we can even arrive to obtain this other large peak and so on. So, but typically for absorption, you are interested in the first, in the lowest energy window. So you don't ever need to include so many eigenvalues. But one thing that you can try is to run different SLEP-C calculations with increasing the number. And then you see that more and more you reproduce this spectrum. So what are these peaks? These represent absorption of photons by excitons, by electron hole bound states. And so we have here 2 excitons, basically. These first 2 peaks represent the first 2 excitons that are able to absorb light. And so then this is the main thing of the tutorial, to test the diagonalization. And here you can also try, for example, different types of precision in the Haydock solver, and as I said, a different number of eigenvalues in the SLEP-C. But if you diagonalize the system so that you also get access to eigenvalues and eigenvectors, so not with the fastest one, but yes, with the full, and yes, with the SLEP-C that is almost as fast as Haydock, then you can also use these values to plot physical quantities related to the excitons. For example, the last part was about the excitonic wave function. You see the excitonic wave function is a linear combination of the wave function of the electrons that are forming the exciton. This is the wave function of the electrons in the valence band at position RH, H is for hole, and this is the wave function of the conduction electron at position RE, E for electron. And you see it's a linear combination weighted by the excitonic eigenvectors. So in our iterative calculation with SLEP-C, we have access to the first 10 states and the first 10 of these coefficients, okay? And what we want to do, so we cannot really plot this because it's a complex number that depends on 6 variables, 3 for electrons and 3 for hole. But what we can do is that we fix the hole to a convenient position, we take the modulus square, and we plot the intensity related to the electron position. This is like the condition probability that the electron will be at RE given that the hole is fixed at R0. So that's the physical meaning. And you can do this with post-processing of Yambo of Yambo. Now I'm just going a bit fast. The first thing that you can do is to print the eigenvalues that you have calculated, right? And remember, in this case, we have calculated 10 of them, so we have 10. And here you can analyze, for example, on the first column, the left column, you have their energies, and you see that they go 2 by 2, same energy, basically, apart from numerical uncertainty. Same energy. These are doubly degenerate states, basically. And here you have the intensity of the peak that is associated. to these states. And you see that the first one is 0. So the first one is prohibited by the selection rules to couple with light. But the second one is not 0, and this is responsible for the first peak in the absorption. And this is typically what we do when we do this kind of calculations. Now we decide, okay, we are interested in this one because it's the one that is bright, the one that you can see as a peak. We want to plot the wave function of this one. So I skip this part because we won't have time, but basically you need to generate another input for post-processing. And the final result would be a representation in a real space with an iso surface of your exciton wave function. And here we have a fixed, as I said, the whole position in a convenient point, which is between in the middle of the MO-S bond. And then what is the condition probability to find the electron? You find it in the area around the hole, but only on the molybdenum atom. And if you check these shapes of the isosurfaces, they look like D atomic orbitals. And this is because these conduction electrons are hosted in the D bands of the material, so that is very neatly visualized in this way. Okay, so basically this would conclude the tutorial. I suggest if you have some time, you have 5 minutes, but if you completed the first part, I suggest that you try at least one type of diagonalization. You can choose which one. For example, you could try the SLAP C with 100 eigenvalues, and you try to do one plot of the absorption spectrum. If or you do later at home, I don't know. But let's just to bring to a conclusion that is a bit satisfying because you will see a plot. And I think for now that's it. And yeah, I mean, of course, we are here for the questions. So now and also up to lunch. About this and also about every other topic that we covered in these 2 days.